field programmable gate arrays or whatever. But there are times when you still have to connect whatever microcontroller to the outside world, and you want to do some type of quick logic, some ANDing and ORing. So you still have to know how to use these chips. You might say they're called the glue logic because you sometimes need to interface something to something else, and you use these things as what would be called the glue. So, but it doesn't matter when you're dealing with these or with complete microcontrollers. You have to understand their drive capability. For example, you're going to, the homework assignment for next Monday is to use your Arduino. First, did everybody see that come through on Canvas? Does that stuff work okay? Or did I guess I didn't put it on Canvas. I did that on. Still trying to learn Canvas. But, so for Monday, I want you to use your Arduinos, get them going, and then you're going to blink an LED on and off at half a second. So you turn it on an LED. You suppose you could hook that microcontroller up to a light bulb and have it control it. Could you have your microcontroller blink these lights? Yes. You can't just interface the microcontroller to the lights. First of all, the voltage levels are all much different. But it's a power issue or a voltage current issue, so you have to be concerned about, can you, again, interface things directly. Okay. So let's go through and talk about CMOS logic. We started there last time. So this is the symbol for an NMOS device. Gate, drain, and source. I put up another symbol for that last time, but we'll stick with this. You generally see this type of symbol here. And the way it is constructed is that you have a P material. P is silicon, and then an impurity is added to it that have holes as the mobile charge carriers. And then we're going to put an N material here, an N material there. This guy will be we'll call that guy the source, this guy the drain. And then on top of the P material, we're going to put a silicon dioxide layer. And silicon dioxide is what? Glass. Okay, so it's an insulator. And then we'll put an aluminum electrode on top of that. So this guy is going to be called the gate. So here's the drain up here, the gate, the source. So it has a family of curves. We could talk about the V, drain to source. The controlling element is the voltage gate to source. So down here, the V gate to source is equal to 0, and then it goes all the way up from there. Okay, and this is our drain current. So right in here, though, it's rather interesting that this guy looks like a resistor. So the drain to source resistance on looks just like a fixed resistor. Okay. Everybody all right with that? Okay, so you don't have to worry too much about this curve here. I'm going to give you the two parameters. We're dealing, well, there's three regions of this curve here. Down here, so if you're down there, how much current is flowing? 0. So we would say the switch is off. Okay. if we're locked up here someplace, so if we're on a load line curve and we're up here someplace, then you would say that the switch is on, and it will have a on resistance of RDS on. Is that right? So in here, which we're not concerned about in this class, we would operate the thing as an amplifier. So any transistor in that middle section is an amplifier. At the two ends, we're using it as a switch. And again, we're talking about in this class a binary system on-off. So for the NMOS, V gate to source equal VCC, VCC being our power supply, then the gate is on and can be represented by a fixed resistor RDS on. If the gate to source voltage is 0, then it's off, and we would represent it by infinite ohms, and it truly is infinite ohms. Well, up in the 10 to the 14th ohms or something like that, close enough to infinity. So is everybody all right with that? We're going to use this thing as a switch. So if you put a gate to source voltage of VCC, we say that the switch is what? On, and we represent it by what? Just a resistor. Okay. If the gate to source voltage is 0, then what? It's an open circuit. All right. If it's in between, like say the device is used as an amplifier, and we don't want to be in that state, somewhere as it is switching from a gate to source voltage from 0 to VCC, that resistance is going to change from RDS on to infinite. All right. Okay. Okay. Well, for a PMOS device, things reverse around. You can, for a PMOS device, the symbol looks like this: drain, source, gate, and our arrow is pointing in. You can keep the exact same curve I gave over there with all the same positive voltages and currents if you swap the subscripts around. So if the source to drain voltage is positive when the source to gate voltage is positive. All right. So here, if for a PMOS, if the source to gate voltage is VCC, the device is on, and it's on with an RDS on. And what do you suppose is going to happen if the source to gate voltage is 0? It's going to be off. Everybody okay with that? Okay, so let's take a look at we talked about resistor transistor logic. What would happen if I did this? I've got a resistor here, and let's say that's 1 kilo ohm. And I'm going to put a resistor, or excuse me, a transistor in like so. What type of transistor did I put there? NMOS or P? N? Is that all right? All right, and I'm going to say that this is my output here. So if my gate to source, well, what voltage is at the source? Kind of a trick question. Where's the source? Here? That's what? This guy, big G says it's the gate. This must be the source. The source is always associated with the arrow, right? Okay. So what voltage is at the source? Ground. It's just ground. So if my source to gate voltage is at 0 volts, is the device on or off?
Off.
Say it again. How many for off? On? Good. It's off. Okay. So that means we represent this switch by what?
Insert.
An open circuit. Therefore, what is V out? VCC. Why? If you have a battery like this and a resistor, what's this voltage? VCC. Isn't that exactly, I mean, it's just drawn a little bit different here, but isn't that the same, right? Okay, so VGS equals 0, V out is VCC. Now, let's let VGS equal VCC. Is the device on or off? It's on. And so what is my V out? In reality, it is going to be VCC times RDS on over my R plus RDS on. Okay. These small, this is, better change things up. These small transistors that we're going to use for a logic level typically have an RDS on of 400 ohms, approximately. So is this good or bad in this case here?
It's not great.
Not great. About what would your output voltage be? About a third of VCC. Why? What's RDS on? What's R? What's 400 over 1400? About a third. Yes? Understand? So this is not good. Okay. What happens if I make this instead of 1K, I make that 100K ohms? What's 400 over approximately 100K times VCC?
4 tenths of VCC.
Wait a minute.
Oh, 0.004.
Yes. And that's about what then? Okay. Get out your calculators. You can't do this in your head. Do 400 divided by 1,004,000 and multiply that by, let's let this be 5 volts. So 400 divided by 1,004,000 times 5 volts, and what do you end up with? 200? 200ths. Okay, what's that equal? About 0. Everybody okay with that? Okay. So, as long as R is much, much, much bigger than our RDS on, this is going to be approximately 0 volts. So what have I made here? back to logic gates, 5 in, 0 out, 0 in, 5 out. What do I made an inverter, correct? Yes? Okay. So this is NMOS type of logic, where you go ahead and put in resistors. Resistors are incredibly real estate consuming. It takes a lot of chip area to put a resistor in. It takes almost nothing to put in transistors. Feature sizes on those transistors there is down in the 10 to 20 nanometer range. Tiny stuff, okay? Used to be 30 years ago, it was down in the micrometer range, but it's even gotten much, much, much smaller. Moore's law says that, you know, every 18 months, the size of the transistor shrinks in half. That has gone away now. We finally got to the end of Moore's law. But, okay, so let's try something different here. Now I'm going to take okay, what is the top device? PMOS? Where is its source? Top. Where is its drain? Where is its gate? Over here. Oh, sorry about that. Okay. Yeah, I messed up on that symbol up there is correct. This one is wrong. I need you want to show that there's a silicon dioxide. Sometimes they put that in or not, but I like to put it in there to show that there's a silicon dioxide. How big do you suppose the width of that area is? How much silicon dioxide are we going to put in? A lot? No, because we're trying to keep these things small, correct? So what do you suppose happened? Well, what have we formed here now? If you take a look at between the gate and the source, I've got a conductor, correct? I've got an insulator and another conductor. What have I made? Capacitor. Okay. You've made a capacitor. So this capacitance here between the gate and the source is about 3 picofarads, something along that line. Is that okay? All right. So we've got the gate here. So I'm going to tie these gates together. Doing okay? And here is going to be my output. So let's let this be VCC here. For the NMOS device, is it on or off? What's its gate voltage? Wait a minute, I've got it listed right there. How much voltage is at its gate? VCC. What voltage is at its source?
Yeah.
Ground. Ground is 0. What is the gate to source voltage? VCC. Is it on or off? On. Well, that was the easy one. That took forever. Take a look at the PMOS device. What voltage is at